Now, first of all, good afternoon for everyone. It's a pleasure to introduce our colleague, Martino Garonzi, who will talk about the alternate group as a product of four conjugacy class. Please, Martino.
Thank you. Okay, so I will talk about joint work with Attila Maróti that we submitted earlier this year. And okay, and it is about alternating group as product of four conjugacy classes. Now, first I need to introduce the motivation and history. So in 1992, Babai and Serres conjectured that if G is a non-abelian simple group, then the diameter of any Cayley graph of G is bounded above by the logarithm of the size of G raised to the power C for some absolute constant C. Okay, and let's reformulate this in a simpler way. We can say that this number, log of order of G to the power C, is an upper bound for the minimal positive integer m, such that the S, okay, it will be S to the m, but we need to add the inverses, or we could choose a symmetric generating set. So this S union S inverse to the m is equal to G for every generating set S of G. So this is the conjecture, and essentially this was open for many years and is still open. And then, for example, solving the Rubik's cube in the smallest number of moves is equivalent to finding the diameter of some Cayley graph. Okay, so this is just an example. Also because I realized that Rubik is Hungarian. When I was here, I didn't know that he was Hungarian, and he's still. By the way, he's 70. He's about 70 now. So, okay, so I just repeated Babai's conjecture here, and until now, Babai's conjecture was proved only for groups of Lie type of bounded rank, leaving still unsolved the alternating groups and the groups of Lie type of unbounded rank. By the classification of the finite simple groups. So essentially, the only case where it was solved was for groups of Lie type of bounded rank. So in other words, the constant that you see there, yes, there exists such a number C, but it's not a constant, it depends on the rank. And who proved this? So, okay, first, the first result in this direction was given by Helfgott. It was a breakthrough in 2008, and he proved Babai's conjecture for PSL2P for P prime. And then in 2010, Babai's conjecture was proved for all simple groups of Lie type of bounded rank, exactly, by Piber and Szabo, and independently by Brogliard, Green, and Tau. Essentially, it was announced simultaneously, this result by them. So, yes. So the bounded rank case is proved, and this has to do with growth of subsets. So the result is that essentially they look at whether a subset A to the 3, for example, they have a result that says that A cube, the size of A cube should be either is equal to G, or it should be, the size should be at least the size of A to the power 1 plus epsilon. So growth, this is called growth. And okay, and then I want to just mention this paragraph is what I want to mention quickly, that we have a project here which is led by Professor Piber to prove Babai's conjecture for some families of simple groups, PSL, PSU, and PSP, so the linear, unitary, and symplectic groups of unbounded rank, of course. I mean, the bounded rank case is done, but under the restriction that the generating set contains a transvection. Essentially, this was done last year by Zoltan Halazi for the groups PSL and P, where P is a prime, but it was not yet for the case where, for example, P is not a prime, but a prime power. Okay, so now I will move towards the result that I want to talk about. So a normal subset of a group G is a subset S such that it is closed under conjugation and by elements of G, and a subset is normal if and only if it is a union of conjugacy classes, of course. And note that any normal subset generates a normal subgroup. Therefore, in a non-abelian simple group, any normal subset distinct from the trivial set is a generating set, and it makes sense to consider Babai's conjecture in this particular situation. So, okay, so it makes sense to consider Babai's conjecture for the generating sets that are normal sets. Now, Liebeck and Shalev in 2001 note that this is a very particular case of Babai's conjecture because we are looking at some particular generating sets. And Babai's conjecture, if you remember, it is about all generating sets. They proved, Liebeck and Shalev in 2001, that if S is a non-trivial normal subset of G, then there is an even better bound. Remember that the bound of Babai's conjecture was log of order of G to the power C. Now the bound that we have here is C times log of order of G divided by log of order of S. So it's much smaller. In other words, you can reformulate this saying that the last sentence that you see here, if there exists a constant C such that for every non-abelian simple group G, you have that if the size of S to the K is at least order of G to the C, then S to the K is equal to G. So yes. For every K that verifies this, we have that S to the K is equal to G. And it makes sense to, if you look at this particular formulation, it makes sense, and in fact, it was considered the case when instead of having S to the K, you can have different sets. Okay, so it is natural to ask whether the same thing holds when instead of K copies of S, we have distinct normal sets. Gill, Piber, and Szabo proposed a conjecture that was later proved by Maróti and Piber, which is the analogous where instead of one set, you have some possibly distinct sets. There exists a constant C such that if S1 to up to Sk are normal subsets of a non-abelian finite simple group G, and instead of the size of S to the K at least order of G to the C, we have this condition here. So the product of the sizes is at least order of G to the C. Then the product of the S size is G. Okay. Now, in simple but less formal words, this says that if we have large normal subsets of a non-abelian simple group G, then their product equals G. So, and this is the spirit of this kind of result. The product of large sets is equal to G. And in this spirit, we proved the following result that is about the alternating group. So consider the alternating group on n letters, and for any epsilon at least larger than 0, there exists a natural number n such that whenever small n is at least big N, so when n is large enough, and A, B, C, D are normal subsets of the alternating group of size at least order of the group to the power 1/2 plus epsilon, then the product of these normal subsets is equal to the group G. And moreover, the constant 1/2 is best possible in a sense that I will explain later. Now, this says that if you have 4 large subsets of AN of the alternating group, then their product must be, okay, I mean, normal subsets, large normal subsets, their product must be G, the group alternating group. And this is the same, in the same spirit as what I said previously. The product of large normal sets should be equal to G in a simple group. Now, this is not saying only that the alternating group is a product of 4 normal sets. It is saying that whenever you have large normal sets, their product is G. Okay, so what I want to do essentially is to show you how this is proved. And but before doing that, I need to talk a little bit. I mean, not. I hope that. Okay, wait a second. I hope that I will say something interesting for all of you. But yes, I just need to talk a little bit about what is needed. So a complex representation of a group G is a homomorphism from G to GLV, where V is a complex vector space, and it is called finite dimensional if the dimension of V is finite. And then the notation is V to the G for the action. And the space V is called the G module. And the complex representation of G is simply a CG module, if you know what that means. A subspace W of V is called G invariant if it is G invariant. So small w to the G always belongs to big W whenever small w is in big W. And the representation rho is called irreducible if the only G invariant subspaces of V are the trivial ones. And we only work with finite dimensional representations, and the character of the representation rho is the trace map that is defined here. Trace is the sum of the diagonal entries of a matrix, and the rho of G can be seen as a matrix. But in any case, this is well defined. Okay. And then we have an easy example here, which I will not talk about much, but if you in C3 you can act, S3 can act by permuting the coordinates, and this gives a representation of S3. So this is like the easiest example. Essentially, it's written here. The action of the permutation sigma is by permuting the 3 coordinates, and this gives linear maps. So any permutation of the 3 coordinates gives a linear map, and you can see in what sense. So the identity goes to the identity, and then you have these things. And then I computed the traces here. Okay, and then this admits an invariant subspace. So this representation is not. So if you look at this, the permutation of the coordinates does nothing. So this is G invariant, and so rho this is not irreducible. But we have some facts that are very well known. I'm just recalling these facts. And so if rho is a representation, then V is a direct sum of, so G now is a finite group, I should say. Okay. And V is a finite dimensional G module. And V is a direct sum of irreducible G invariant subspaces. This is Mass-Case theorem. And then the trace, the characters are class functions. So, which means that if I apply the character to a conjugate, it doesn't, it's invariant by conjugating. It's written here. And then two representations of G are called equivalent if the corresponding G modules are G isomorphic. In other words, there exists a linear isomorphism from V1 to V2, preserving the action. And two representations of G are equivalent if and only if they have the same character. This is very important. The number of characters is equal to the number of irreducible representations of G up to, I mean, the number of, I mean, you can decide whether two representations are equivalent by only looking at the character. Okay, and the character, by the way, is called irreducible if the representation that it is the character of a representation, and it is called irreducible if the representation is irreducible. And there is a bijection between the set of conjugacy classes of G and the set of irreducible complex characters of G. And so the number, in particular, number of irreducible characters is equal to the number of conjugacy classes of G. Now, and then it is interesting to ask, and this is what we will also need, whether I mean to ask what are the irreducible characters of a group. And in particular, I'm working on with the alternating group. So, and in particular with the symmetric group, because the alternating group lies inside the symmetric group. So I want to tell you briefly what are the irreducible characters of the symmetric group. Because essentially, if you look at our proof, essentially, what do we do? We apply character theory. I will explain how. By knowing, and then we manage to do everything by simply knowing the values of the characters of the alternating group. And of course there are other things that are needed, but essentially this is one very important part of the proof. So I want to tell you how what they are. So a partition or Ferrer's diagram or Young diagram lambda of n. The notation is this one. Is a disposition of n boxes in a number of horizontal files so that the number of boxes in a given file is non-increasing. Now, so essentially you have n boxes, in this case 23. And the first line has 7 boxes, the second has 5, and so on. And the number in each the following file is not non-increasing. Now, a hook, gancho in Portuguese, is a partition of n of this type. It's easier to see from the picture. See, so this one is a hook. These ones are hooks. It means that the horizontal files starting from the second all have size 1. So the first line, it doesn't matter, but the other lines should all have size 1. And the upper left-hand box of a hook is called the head of the hook. So where you see the number, this box is called the head of the hook. And usually we write the length of the hook on its head. So for example, here 5 because 1, 2, 3, 4, 5 boxes. 4 because 1, 2, 3, 4 boxes, and so on. The leg of the hook is the set of boxes below the head. So for example, here 3, right? This hook here, sorry, this hook here as length, the leg is as length 3. And for this hook, for example, the second one, the leg as length 0. And the arm is the set of boxes at the right of the head. So for example, for this hook, we have the arm that has length 4. Okay, that's what I said. I mean, this is the definition of hook. This is a particular partition, and okay, so wait a second. Then, given a partition lambda of n and box of lambda in a position ij. So, for example, 11 here is in the position 1, 1, 10 is in the position 1, 2, and so on. Hij is the length of the hook contained in lambda, whose head is the box ij. So, for example, why is this a 7? Because if you look at how many boxes are there? 1, 2, 3, 4, 5, 6, and 7, right? And this 8 is because 1, 2, 3, 4, 5, 6, 7, 8. So every box is a head of a hook, and the number is it's called Hij, is the size of this hook. Now, the rim of a hook, borda di un gancio, contained in a given partition, is the set of boxes that form the, okay, I try to explain here, form the external part of the area detected by the hook. But it's easier if you look at the picture. So this is the head, and then you have the hook, which is given by the bullets. Okay, and then the rim of the hook, hello? And then the rim of the hook is this part, external part here. So this is called the rim of the hook with head H. Okay, so and the hook and its rim always have the same length. 1, 2, 3, 4, 5, 6, 7, 8. Yes, I mean, this is easy to see that the rim of the hook and the hook have the same length. Okay, so this is the rim of a hook. And why am I introducing all this? Okay, because I need this to define, to define functions that will be the characters. Now, if we have two partitions, so lambda and mu here, two partitions, a path in lambda associated to mu is the subsequent removal of the rim of a hook of length mu I for I from 1 to k. So as usual, it's easier if you look at the picture. So in this partition mu, you have 4 lines, and then what you have to do is remove the rim of a hook on the left, but it should be of the same length as the first line of the second partition. Then after you remove this hook, this rim, you have to remove the second rim, and then after you, which corresponds to the second line of the second partition, and so on, and continue this way. So this is called a path. This is a subsequent removal of this type. So in this case, you have two partitions, as you see, and you have to do subsequent removal of rims of hooks. And then you define L of P. So this is a path, let's call it P. And you define L of P to be the sum of the leg lengths of the hooks in the path P. Okay, so this is L of P. So you have a path, which means subsequent removals corresponding to a partition lambda and a partition mu. And then you do the sum of the leg lengths of the hooks in the path. Of course, if you have two partitions, there is not only one way to do the removal. There may be more than one path. So this is just saying what are the lengths, and this is the length of this path. Why 3 plus 4 plus 5 plus 0? Because, for example, if you look at the first removal, this is the hook whose rim is red, and the leg length is 3. Now in the second removal, this is the yellow one. This is the hook whose rim is yellow, and the leg length is 4. So this is why the 4. And then the green one has wait a second. Maybe it should be a 4. Maybe. Anyway, yeah, I think it should be a 4, not a 5, right? 1, 2, 3, 4. Yes, should be 4. And then for the last, you have 0 because this the length of this, the leg of this length is 0. Now, so this 5 should be a 4. Okay, so and why all this? Okay, now we finally get to the point. If you define a function chi lambda from G to C in this way, G now is the symmetric group. Okay, so this is a strange sum. This is the sum over the paths of -1 to the power length of the path, which was defined before. This is called the Murnaghan-Nakayama rule, and these, as you imagine, they turn out to be precisely the irreducible characters of Sn. So this is the formula that defines. So the reason why I explained to you these things with pictures is to explain how to compute the characters of the symmetric group. And the sum is over. Yes. So where do we take these paths? So remember that lambda is fixed, but who is mu? Because if you remember, let's go here. These paths corresponded to 2 partitions. One was lambda, and the other one was mu. So here we have lambda, and then we have a G. So mu is the shape of G. So, for example, you remember that an element of Sn has a cycle structure. So this determines a partition. You can think about it as the orbits of G, of the small g. So this determines a partition. And this partition, you can see, has a Ferrer's diagram or Young diagram. And then you have a partition. So now you have lambda, and then you have the partition associated to G. If there are no paths, then the sum is empty, and chi lambda of G is 0. And then we have a formula for chi lambda of 1, which is not immediate, of course, but this is called the hook length formula, and this is also useful because you can compute all these are essentially the degrees of the irreducible representations of Sn. And I mean, this is important in my opinion, these kind of things, because somehow it is not also, it's not very easy to find these kind of things in the literature. I mean, as I said, I'm basing this material on the book by James and Kerber. On the other hand, somehow it's hard to read these things on a book. I mean, I think it's easy. I mean, I think that talking to people about it is kind of easier somehow. I don't know, but anyway, so I think this is very important. Okay, and then as I said, the functions chi lambda are the irreducible characters of Sn, and the trivial character corresponds to the horizontal hook, and the sign character to the vertical hook. Now let's do some. Okay, this is an example of computation of chi lambda. Okay, so I will do this quickly. You can have this partition and this other partition, the cycle type of G, and there are 2 paths in this case. One is by first removing, the lower rim and then the upper one, and then you can also do the other way around. So we have 2 paths, and then you can compute by the formula, you can compute chi lambda. So this is just an example to say that given 2 partitions, you can have more than 1 path. Now, the example is, okay, S3, again, quickly, I mean, S3, you can see that for every partition, you have a corresponding partition on the upper hand side. Essentially, this column has the characters and this row has the cycle structures of the element of the conjugacy classes. And by applying that formula that I said, you can find the character table of S3. And then if you look at S4, this is maybe more interesting because you can see that, for example, if you know a little bit of character theory, you can see that trivial and sign, they kind of are dual of each other. And also these two are dual of each other. This is kind of playing Tetris. You know, if you play Tetris, these are the shapes. And you can see that essentially when you do character theory, you can, in this case, you can conjugate a character, do the complex conjugation, or in other words, you can, okay, wait a second. I don't want to say, okay, I will say it like this because it's better, but what I want to say is that, for example, if you have this character, you can do the tensor product with this other character, and this has the effect of symmetrizing this picture. So this goes here, and so you can look at dual characters to be like one desymmetrized of the other, and this is interesting in my opinion. And what happens for the alternating group? I want to say for just a second that in the alternating group, okay, these two characters, trivial and sign, when you restrict to the alternating group, they are equal, okay, because the sign in the alternating group is always 1. And the same thing happens for these two. So essentially, when you have two characters which are dual of each other, geometrically one is desymmetrized of the other. Then when you restrict to the alternating group, you have that they are the same, and also that's in an irreducible character of the alternating group. On the other hand, if you take this one, which is called self-adjoint or symmetric or something, self-adjoint, when you restrict it to the alternating group, you get two characters. I mean, you get a character which is a sum of two characters, of two irreducible characters. And okay, so let's see. And then this is explained. Okay, so, sorry, this is just a proposition, I mean, an observation that yes, so because I will talk about it later. So if lambda is not a hook and G is an n cycle, then chi lambda of G is 0. And this is because if your partition is not a hook, then the only way you can have a path is when the other partition is the other partition. No, I'm sorry. If you have on the left lambda is not a hook and G is an n cycle, then there are no paths, because in order to have a path, you need to have a hook corresponding to this particular partition. You need to have a hook. I mean, this is the only way that you can remove a rim of length n. I mean, there is no way to remove a rim of length n unless you have a hook. Now, what I was talking about was the irreducible characters of our alternating group. And I will say this quickly, but essentially this has to do with self-adjoint partitions. so symmetric partitions, as you can see here. And now yes, essentially what happens is that what I was saying, that if you have a partition and this is not symmetric partition or not self-adjoint, then its restriction to an is an irreducible character of an, and if you do the same with its symmetric, you get the same character. On the other hand, if it is self-adjoint, the partition, so it is symmetric. Remember, when I say self-adjoint, you have to think about this kind of partition here, so which is symmetric with respect to this diagonal, right? That you saw also in the character table here. You had, for example, this one, that was a square, and then in this case, the restriction is a sum of two irreducible characters, which we could call chi lambda plus and minus. Okay. Now, now this part I will probably not talk about. I mean, I included this because it gives precisely the value of the characters for the alternating group. So I figured that it's useful to have everything in the slides, but now this is less important. So the reason why I introduced this is because I wanted to give an idea of what are the tools that we use. And now, essentially, there is a way to compute all the characters of irreducible characters of the alternating group and symmetric group. And now I will say why we need all this. So to prove our results. So now, if denote by Ir of G to be the set of irreducible complex characters of a finite group G. If A and B are conjugacy classes of G, we are interested to know which conjugacy classes the normal set AB contains. So this is one of our arguments. We have a product of conjugacy classes is always a normal set. So if you have two classes A and B, conjugacy classes, then A times B is always a normal set. It is a union of conjugacy classes. Now, if you fix an element small a in A, small b in B, and G in G, then this is the point where we use character theory. The size of this set here, the size of pairs in A times B such that X times Y is G, is equal to size of A, size of B divided by size of G, multiplied by this sum here. And this sum is the sum of the irreducible characters of G. So you can see here that essentially what we want is that this number is non-zero, because we want to say that the small g can be written as a product of an element of A and an element of B. And this is an exercise in Isaac's book, problem 3.9, if you're interested in Isaac's book, Character Theory of Finite Groups, proves that we have this equality. So essentially we are deal with this sum here, and we have to prove that it's non-zero, right? And how do we prove that this sum is non-zero? Okay, so yeah, this is what I said. So G is contained in the normal set. So G is contained in the normal set AB if and only if this sum is non-zero. Okay, and how do we prove that this is non-zero in the case that G is the alternating group? The strategy is to show that this condition one, to prove that it holds, is to separate the contribution of the trivial character. So in this sum, we separate the contribution of the trivial character, and the contribution of the trivial character is 1. And then we show that the remaining part tends to 0. So this can be written as a 1 plus the sum over non-trivial characters of the same thing. And then we prove that it tends to 0 when n tends to infinity. Now, this is done. Okay, so what I want to say is that when you do such computation, you apply the things that I said about characters of the alternating group. And in particular, if the element G is an n cycle, which is our situation actually, we are interested to know whether an n cycle belongs to such. I mean, this G for us will be an n cycle. Then this is a strong restriction on the characters that can appear here, because if you remember, I said that the partitions associated to this character, such that chi of the n cycle was non-zero, had to be hooks. So essentially, if G is an n cycle, then we can this sum it is actually over partitions which are hooks. Okay, so yes, and the other central idea, so this is one idea, character theory, and then there is another central idea, which is the following. So if C is a conjugacy class in the symmetric or alternating group, we denote by delta of C n minus t, where t is the number of orbits of the small x, where x is an element of C, and delta of C is the number of orbits on the set of n points. And now On denotes the set of n cycles, which is a conjugacy class in Sn. Now we will look at the case when n is odd, because the case n even is similar. And if n is odd, then On is contained in An, in the alternating group, but it's not a conjugacy class. It's a union of two conjugacy classes in An. Now the result that we need is the following. If A and B are conjugacy classes of Sn contained in An, and we have this condition where delta was defined here. So for every class, we have delta of the class, which is n minus the number of orbits. And if this holds, then AB contains On. So this is a criterion to know whether On is contained in a product of conjugacy classes. Now, note that these A and B are conjugacy classes in Sn. So we need to somehow work out what happens with An, because we are interested in An. And but in any case, in order to apply this, we need to relate it to largeness. Remember that we are working with large conjugacy classes. So if you have gamma and epsilon, two positive constants from between 0 and 1, then when n is large, okay, so there exists a big n, such that for every small n at least big n, and X is an element of the alternating group, which has very large, which has large conjugacy class, in the sense that the size of X to the G is at least order of G to the gamma, where gamma is here. Then delta of the class can be bounded below by gamma minus epsilon times n. Now the idea of this lemma is that if the class is large, then delta is also large, okay? So this is the idea. So if the class is large, then delta of the class is also large, okay, essentially. And this immediately implies the following. So here I just copied the two results that were above, okay. Now imagine that you have two classes, A and B, and write them like this, the orders of them, their orders. And then what you can say is that, okay, and assume that if you remember, in our statement, we had the order of A and the order of B, their product was at least the order of G to the 1 plus epsilon. So this can be translated into this. Gamma 1 plus gamma 2 is at least 1 plus epsilon. And then we use that if the class is large and then delta is large, and then we compute and we find exactly that the sum is larger, is at least 10. If you apply this result but to epsilon over 2, I mean you find that sorry, maybe this gamma should be a delta. Sorry, yes. Sorry, this is a delta, okay. And so if you do delta of A plus delta of B, then using what is written here, you find that it's at least 10, and then if this is at least 10, then AB contains ON. So this is the other type of argument that we use. Now, okay, so. Now, of course, so this argument is very strong, but there are cases that are different, so they need to be treated differently. And before explaining the proof of this, I will talk about this 1/2. So recall that this is our result. So let AN be the alternating group. For any epsilon at least larger than 0, there exists an N, such that whenever N is at least N, so is large, and A, B, C, D are normal subsets of AN of size at least. So when I said, for example, that the size of A times the size of B at order at least order of G to the 1 plus epsilon, is because they individually have order at least this. So yes, so I mean, like this 1/2 plus epsilon, when you sum two of them, you get 1 plus 2 epsilon. So this is why I had a 1 plus epsilon here. Okay, so this, I applied this to the product. Now, okay. Now, before and then, if this happens, then ABCD is equal to AM. And before giving an idea of this quickly, I want to say what do I mean by saying that 1/2 is best possible. And the reason is that there exists a conjugacy class in AN when N is a multiple of 4. A conjugacy class C that is the class of fixed point free involutions that has size at least 2/3 to the N times the square root of the order of G. And this implies that the order of G is arbitrarily close to the square root of the order of G. And on the other hand, C cube is not G, showed by Brenner, and C to the 4 is G. So essentially, this is to say that if you hope to have something like 1/2, I mean, essentially what I mean is that if you want to hope to have some constant of the type 1/2 or close to 1/2, then you cannot get. Essentially, you need 4. You need 4 sets. 3 is not enough. Okay, so this is what I mean. Maybe I don't know if it's clear. I mean, it's also not easy to state, but what I'm saying is that if you want to have a constant close to 1/2, then 3 classes are not enough. So this is why the 4. Okay, this is why we need 4 classes. Essentially, this is a kind of a motivational argument. Now, first of all, we give an idea of the proof. Okay, quickly. But of course, we need to use all the things that I talked about until now. So I mean, from the beginning, I actually am giving arguments for the proof. So first of all, we may assume that A, B, C, D are conjugacy classes. Recall that in the statement they are normal sets, and we may assume that they are conjugacy classes. And why? Because every big normal set should always contain a big conjugacy class. And this is a principle that has to do with the number of classes. So if you look at a big normal set. It is a union of conjugacy classes. On the other hand, the number of classes is small in the alternating group. The number of classes in the alternating group is very small, 2 to the n, at most 2 to the n. So when we say large, we mean order of g to some power. Now 2 to the n is much smaller than order of g to some power. So this means exactly that every big normal set, every big union of classes should contain a big class, right? Now, in this first slide, I mean, there are a lot of things, but what I want to say is simply that if you remember, we had a character theoretical argument. So first of all, we want to show that if A and B are exceptional classes. Now, don't worry about this word exceptional. I mean, but exceptional classes, it means that they are classes in AN, but they are not classes in SN. And if A and B are exceptional classes, we want to show that AB contains ON for n large, okay? And how do we do this? By using, if you remember, we had a character theoretical argument for this. And it involved proving that this was non-zero, okay? And how do we do this? The sum here is over the non-trivial irreducible characters corresponding to n hooks. Because if it doesn't correspond to a hook, we saw that the value was 0. And non-trivial because we want to bound the sum of the non-trivial ones, because the trivial gives a contribution of 1, which is very large. So we want to show that the rest goes to 0, as I said. And how do we do this? Okay, we need to use some results, Larsen and Shalev in particular. And so essentially, I mean, this is a computation that I wrote to give you the idea of how these things work. But at the end, when you work out cases, you can either, I mean, occasionally you need results that are in the literature, and occasionally you need to compute a character value using what I said before about partitions and hooks. And then by doing this computation, you show that you get a number that goes to 0. So this is the character theoretical argument. And I mean, it's not particularly hard to prove, but when n is large enough, On times On is G, and probably even for every n. I'm not sure about that. I would need to check. But G now is the alternating group, okay? And okay, so combining all the things that I said, we can give the final argument. So this is the final argument. So first of all, we have that On times On is G. On is the, remember, On is the set of n cycles, and then is all now. This was proved by Dwyer and Rogers. And then using character theory and the results of Dwyer and Rogers about delta of a class that I explained, we find that the product of two large classes not contained in On contains On. If C is a class of n cycles, then On times C is G, and the product of three classes of n cycles equals G. So we have these three facts. Okay, so using this, we can prove that ABCD is G, right? And the idea is that if at least 3 of the classes consist of n cycles, if at least 3 of these 4 classes consist of n cycles, then we can use this fact, because product of 3 classes of n cycles equals G. So, and then we are done. Now, if 2 of them are not classes of n cycles, say A and B, okay, then On is contained in this product by this fact here. And this is the one that I argued, proved, I mean, with the character theoretical argument. And now, if one of C and D is a class of n cycles, so now A and B are not classes of n cycles. If one of C and D is a class of n cycles, say C, then using this, we find that A, B, C, D contains O, N, C, D, G, D, which is equal to G. And then if finally, this is probably also an important case, if C and D are classes of n cycles, then CD contains ON, so AB contains ON and CD as well, and then we have this. So essentially, this is the idea of the proof. I mean, it has a lot to do with containing n cycles. I mean, deciding whether a product of two large classes contains n cycles. I would say that a lot of what we did is about this, deciding whether the product of two large classes contains n cycles. And to prove this, we need on one hand character theory, and on the other hand the results that I explained about, I mean, of Dwyer and Rogers about delta of a class. Now, finally, now we can ask if the same holds with less than 4 classes. So we had A, B, C, D is equal to G, but we could have less than 4 classes. But of course, the product of two large classes is not equal to G, because if product of two classes is G, then AB is equal to G, then AB must contain 1. But this means that the class of B is the inverse of the class of A, okay? There exists an element in B and an element of A, which are inverse of each other. But this means that being large is not enough. If you want a product of two classes to be equal to G, being large is not enough, because, for example, A can be large, but B can be also large, but not equal to the inverse of A, and then AB is not equal to G. So a product of two classes, even if they are large, does not need to be equal to G. But asking whether the same holds for 3 classes is an interesting problem. And we thought about it, and we discussed also with some other people, where, like, I should say that here in Budapest, people are very familiar with character theory. I mean, all the things that I talked about, partitions and characters of symmetric groups, I mean, they are very familiar with these things. But we couldn't find an answer yet. Okay, and here there are some references. Okay, thank you. If you have questions, I'm here.
Let's thank Martino, please. So, ask questions. Does somebody have some questions?
Yeah. So, okay. So my question, the first question is that if I mean, let us take the symmetric group. I mean, it should be known that it can be written as a product of how many classes? Like alternating groups can be written as a product of 4 classes, as you have proved. Yeah.
Yes.
So in the case of Sn, what is the number? I mean.
Yes, sorry, I should have mentioned this, that essentially, if a group can be written as a product of conjugacy classes, then the group must be a perfect group. Because if you can write, yes, if you can write a group as a product of classes, then now you, wait a second, you can do the projection, and then they become elements. Yes, I mean, a product of classes is equal to a coset. Yes, it will be. I mean, Sn is not a product of classes. That's what I'm saying. Yes.
Okay. Sorry. Okay, I understand. Okay. Okay, thank you.
And also, it's a. I think it's a theorem that a group is a product of conjugacy classes if and only if it is perfect. Yeah, it is a theorem, I think, yes. I don't remember who proved it.
Okay, thank you.
Thank you.
Some other question? You said that
yes.
you said that you had a project to prove some aspects of the Babai conjecture. I don't remember exactly you said, but this result gives some consequence in the Babai conjecture in some special case. This theorem that you show for us.
No, this is a kind of this is another direction. The alternating group is another direction of the. I mean, it is related to the Babai's conjecture, but on what I said about our project is this that is here, and we have a lot of work done on this. I mean, it's just that we didn't finish yet, but we have a lot of work done on this. Essentially, for the symplectic group, we have a proof, but for the other cases, I mean, it's a bit more complicated, but essentially, we hope to finish soon this project. And so the alternating group that I talked about today, I mean, is in a different direction because it is a product of distinct sets. And the Babai's conjecture is about the power of a set. So yes, so they are related, but they are.
But in the definition that you said, the product of conjugacy class is equal a group, could you replace normal subset by A to the G inside A instead of J A to the G equal 8? It's possible to change
A to the G. Where?
Inside to
here?
8 is, yeah, because you said that
you mean here?
Yeah, the definition of normal set is A to the G equal 8. You said, no? You can replace it to A to the G inside A.
A to the G is equal to inside. Yes, I think it's equivalent. Yes,
because the groups are fine, right?
Yes,
okay,
but
yes, okay.
No, but yeah, but even if they are infinite, I think. I mean, okay.
So, some other question? No. If not, let's thank again, Martino, please.